What if the metal that still powers most cars on the planet has been quietly poisoning people since the days of the Roman Empire? And we found out too late. Lead built aqueducts, adorned the faces of Egyptians, and today hides in billions of lead-acid batteries, without which cars, elevators, and entire cities would grind to a halt. We'll descend into mines where explosives shatter rock, trace the journey of galena to red-hot furnaces, and discover why this metal simultaneously saves infrastructure and destroys health. Stick around till the end. One fact about lead will forever change how you look at an ordinary battery. Okay, let's rewind the clock and dive into a story that began long before the first smartphones and even before the invention of the wheel. How did people even learn about lead, this sneaky, two-faced metal? Truth is, nobody knows exactly who or when first discovered lead, because it wasn't officially discovered by a scientist in a lab like many other elements. Lead is one of those metals that's just always been around humans, and its history is intertwined with the history of civilizations themselves. Picture this: ancient times, way before people learned to work with iron or even copper. They were searching for interesting stones, clay, anything they could use. And then, in certain places, especially where there are ore deposits, they stumbled upon a really unusual stone. These were lead ores, most commonly galena, lead sulfide, which looks like dark gray, almost black crystals with a metallic shine, often in cubic shapes. Lead ores often lay close to the Earth's surface, and there was plenty of it around. Plus, lead sometimes occurs in its natural, pure form, though that's pretty rare. Lead has an incredibly low melting point, just 621 degrees Fahrenheit. This means you didn't need some super high-tech furnace to melt it down. A good hot campfire was enough, and if there happened to be lead ore nearby, shiny liquid metal could literally just melt right out of it. The metal in the ore heats up, melts, and starts flowing out of the rock, forming little shiny puddles or droplets. This must have been absolutely mind-blowing to witness. Out of stone, without any tools, just from fire alone, this shiny, heavy, soft material appears that you can shape with your hands. You could easily flatten it, bend it, cut it even with primitive tools. It wouldn't break like stone. This made it perfect for crafting simple objects. Archaeological findings show that lead was used as far back as 7,000 or 8,000 years ago, dating to the Neolithic period, for example, in Turkey. People found beads and other small lead objects there. In Mesopotamia, Egypt, and later in Greece and Rome, lead became widespread due to its availability and ease of working with. The Romans built their famous aqueducts and water supply systems using lead pipes. The word plumbing comes from the Latin plumbum, which means lead. Ancient Egyptians used lead sulfide for eye makeup, while Romans used it for skin lightening and in paints. Nobody back then, of course, suspected this metal was toxic. After all, lead poisoning symptoms were often chronic, developed slowly, and could easily be blamed on bad luck, other illnesses, or curses. People just saw a shiny, useful metal that was easy to work with, and they actively used it, never suspecting that beneath its appeal lurked a treacherous enemy. Now that we know the grim history of lead's discovery, let's fast forward to our time. Despite all its toxicity and the massive campaign to phase it out, lead is still part of modern industry. But how is it mined now, and where does it hide when we're so desperate to get rid of it? This is a story about precision, control, and the constant battle against its poisonous nature. Lead, like its neighbor zinc, is rarely found in its pure form. It's mostly extracted from ores, where it exists as lead sulfide, known as galena. And, as you might have already guessed, this anti-hero often shares its deposits with zinc, as well as other valuable metals like silver and copper. The world's top lead producers are China, Australia, the United States, and Peru, which once again overlaps with the geography of zinc mining. The extraction process starts with locating ore bodies. Geologists, armed with cutting-edge technology, scan the ground and conduct exploratory drilling to find spots where galena concentrations make economic sense. Once a deposit is identified, mining operations begin. This can either be an open pit mine, where massive excavators strip away the top layers of earth, gradually working their way down to the ore, or an underground mine, where miles of tunnels are drilled, penetrating deep into the Earth's crust. In underground mines, drilling rigs are used to create holes in the rock, which are then packed with explosives. After controlled blasts that break up the ore vein, specialized loaders gather the ore fragments and haul them to the hoisting shafts. Ventilation systems run at full capacity, removing dust and pumping fresh air down into the depths. All the ore is brought to the surface, where it begins its long journey to becoming a metal ingot. After crushing, the flotation process kicks in. This is a chemical-physical method that separates different minerals. The crushed ore is mixed with water and special reagents in massive tanks. These reagents selectively attach to galena particles, making them water repellent. Then air is pumped through the mixture, creating bubbles that the lead mineral particles cling to and rise to the surface as foam. This foam is collected, forming lead concentrate. The waste rock settles at the bottom and gets disposed of. Since lead and zinc are often found together, different reagents and flotation cycles can be used to separate them individually, which requires high precision and chemical control. The resulting lead concentrate, now containing a much higher percentage of lead, is shipped to the metallurgical plant. This is where it transforms into pure metal. The most common method is pyrometallurgy, which involves several stages. First, the concentrate is roasted in special furnaces at high temperatures. This is a calcination process that removes sulfur from galena, converting it into lead oxide. The sulfur that's released as sulfur dioxide gas is carefully captured and converted into sulfuric acid to prevent air pollution. Then the lead oxide is loaded into large blast furnaces, where it's mixed with coke and fluxes. In these furnaces, at temperatures over 2,000 degrees Fahrenheit, a reduction process takes place. The carbon from the coke pulls oxygen away from the lead oxide, releasing liquid metallic lead. The molten lead, which is extremely heavy, settles to the bottom of the furnace. On top, a layer of slag forms. That's the melted impurities. Molten lead is periodically drained from the furnace, but this isn't pure lead yet. It contains impurities of other metals, such as copper, silver, gold, bismuth, and nickel. That's why lead goes through one more stage, refining. This could be heating to specific temperatures to remove impurities, or electrolytic refining, where electric current separates lead from other metals, achieving very high purity. It's at this stage that valuable byproduct metals like silver and gold, which accumulate in lead ores, are extracted. So where is all this carefully mined and refined lead being used today, now that we know about its dangers? The biggest consumer of lead, accounting for about 85% of all global consumption, is the production of lead-acid batteries. These are the same batteries that start the engines in nearly every car on the road, and they're also used in uninterruptible power supplies, backup power for telecom networks, and large-scale energy storage systems. In electric vehicles, even though the main battery is lithium-ion, there's often still a small 12-watt lead-acid battery to power the onboard electronics. This is a massive market that keeps demand for lead rock solid. Every year, over 500,000 bridges are built worldwide, but only a few of them challenge nature and time. To create a giant capable of withstanding thousands of tons of steel, windstorms, and earthquakes, engineers first dive into the very heart of the Earth, drilling the ground to a depth of over 100 meters, studying every layer of rock. Here, under water and mud, the foundation is born, on which the fate of the entire structure depends. How do machines weighing as much as houses place piles with millimeter precision? And what will happen if even one of them shifts? Watch until the end, and you will learn what the engineering elite keeps silent about. The construction of long bridges begins long before the first steel beams or concrete supports appear. It all starts with a site investigation. Engineers analyze the soil, the strength of the current, the level of seismic activity, and the depth of the bottom if it's a river or a bay. Often, special drilling rigs are used to take rock samples at depths of over 300 feet. These data determine the type of the future bridge: suspension, cable stayed, or beam. After this, a three-dimensional model is created. It takes everything into account: the load from transport, the force of the wind, temperature fluctuations, and even the possible impact of waves during storms. For bridges longer than half a mile, the permissible error in calculations can be no more than a few millimeters. Otherwise, the structure may lose stability. When the construction of a bridge moves from drawings to the actual ground, one of the most responsible and complex stages begins: the construction of the foundation, or the pile foundation. It is these structures, hidden under water or earth, that support the weight of the entire bridge: thousands of tons of steel, concrete, transport, and even wind load. Drilling cranes arrive at the site, giant machines with a long mast, a hydraulic drive, and interchangeable drills. They can reach the height of a 3-story building. Steel piles are brought to the worksite. Usually these are pipes with a diameter from 3 to 6 feet and a length of up to 100 feet. In marshy or marine areas, the piles are even larger, sometimes up to 150 feet. The drilling process takes place in stages. The machine is positioned with an accuracy of a few inches. For this, laser and GPS systems are used. Then the operator lowers the drill into the ground. The powerful rotation of the bit crushes the rock, and a hydraulic system pumps out the resulting pulp. In some areas where the soil is unstable, drilling is carried out with the immersion of casing pipes, metal casings that prevent the walls of the well from collapsing. When the hole reaches the specified depth, a steel pipe, the pile casing, is installed in it. A reinforcing cage is lowered inside, which strengthens the structure, after which concreting under pressure begins. Through a special hose, a concrete mixture is supplied from the bottom up, displacing water or mud. Thus, a dense, air-free mass is formed, which over time hardens into a monolith. In marine areas, floating barges with drilling rigs are used. Divers control the position of the pile underwater, and engineers monitor the process with ultrasonic sensors. In a strong current, drilling is carried out only during periods of calm, when the wave level is minimal. When the piles are installed, their tops are cut to the required height, and capitals are mounted on them. Large concrete blocks that unite several piles into one support. After this, pylons or columns are erected on these foundations, which are already visible above the surface. On land, temporary sites are simultaneously set up. These are logistics centers where beams, cables, reinforcement, and concrete sections are stored. Often, huge cranes 300 feet high are used here, which can lift blocks weighing over 200 tons. When the supports are ready, the turn of the superstructure comes. For bridges of great length, two main technologies are used: suspension and cable stayed. In a suspension bridge, the main load is carried by steel cables. To secure them, two massive towers, pylons, are first erected. Their height can reach 700 feet, as in the Golden Gate Bridge in San Francisco. The towers are assembled in sections, lifting each one with a crane and connecting them with bolts and welding. After the installation of the pylons, the main cables are stretched between them. This is a complex process that is carried out in stages. Thin steel wires, the thickness of a finger, are stretched one by the hundreds, until a main cable several feet thick is formed. Then vertical hangers are attached to these cables. They will hold the roadbed. In cable-stayed bridges, the main load is transmitted through inclined cables that go directly from the towers to the sections of the roadway. Such cables are made of steel strands with a polymer coating, capable of withstanding a load of over 500 tons. They are installed with the help of hydraulic winches, which precisely regulate the tension. The installation of the span sections is one of the most impressive stages in the construction of a bridge, when the giant engineering structure literally begins to connect the shores. Each section is a finished fragment of the road, made of high-strength concrete or steel at a specialized plant. There they are formed in giant molds, reinforced with steel bars, treated in thermal chambers for rapid strength gain, and then marked and checked for accuracy with a laser system. After this, these blocks are transported to the construction site. If the bridge is laid across a body of water, the sections are delivered by barges, floating platforms capable of withstanding hundreds of tons. On land, they are transported by multi-axle trailers with dozens of wheels, which evenly distribute the weight. The movement of such columns is usually accompanied by police, as each block can be from 100 to 400 tons and over 100 feet long. At the construction site, floating cranes or lifters are already waiting. These are powerful lifting systems capable of lifting a load of over 500 tons. Most often, such cranes are mounted on pontoons or mobile platforms that can accurately maneuver over the water. During the lift, the crane operator coordinates his actions with the engineers who are on the bridge supports. Every movement is a matter of inch precision, as the section needs not just to be lifted, but placed perfectly in the design position. When the block is suspended above the supports, it is slowly lowered. Workers fix the position with the help of special guide pins and laser marks. Then dampers and high-strength connecting bolts are installed in the joints of the sections. It is important that the sections fit together without the slightest misalignment. Even an error of half an inch can cause uneven load. Next, the joints are filled with cement mortar under pressure, which fills all the voids and forms a monolithic connection. In some types of bridges, post-tensioning cables are used, steel strands that are threaded through the internal channels of the sections and tensioned with hydraulic jacks, providing additional strength. If the bridge is being built over the sea, the installation is even more complicated. Barges with sections are tied to positions with an accuracy of a few feet using GPS, and the lifting takes place only in calm seas. Often at night, when the wind is weaker and the waves are minimal, the crane slowly lifts a section. The process can take several hours. From the side, it looks like a giant aerial operation. A steel or concrete slab, as huge as a two-story building, smoothly rises above the water or a gorge, moving with an accuracy of a few centimeters. When it is fixed between the supports, the bridge literally grows. Another span, another few tens of feet of road, which bring it closer to completion. In parallel with the installation of the roadbed, communications are laid, lighting systems, communication wires, pipes for rainwater drainage. Most bridges have sensors that measure vibrations, temperature, the tension of the cables, and even the concentration of salts in the air. These data are constantly transmitted to a control center. When the main structure is completed, the road surface work begins. The surface consists of several layers. The first layer is a special anti-corrosion compound that protects the concrete and metal. Next, waterproofing is applied, then several layers of asphalt or polymer concrete, about 4 inches thick. For suspension bridges, lighter materials are used to reduce the load. The final stage is the installation of railings, noise barriers, and the painting of steel elements. The painting has not only an aesthetic function, it also protects the metal from corrosion. For bridges over the sea, paints with the addition of zinc are used, which create a stable protective layer. After the completion of all work, the bridge undergoes a series of tests. Special trucks are loaded onto it to check how the structure reacts to weight. Vibration tests are also conducted. Engineers check how the bridge behaves during wind or the movement of trains and cars. If the indicators meet the standards, the object is put into operation. Imagine, you throw away an old washing machine, not even suspecting that it could live another life. But where does your appliance actually end up after it's been taken away at a discount or for free? Is it really recycled? Or just buried under a layer of earth? Behind every seemingly dead machine stands a whole industry of destruction, separation, and material revival. Giant shredders, magnetic separators, eddy current fields that separate aluminum from steel with centimeter precision. And at the end of the video, you'll learn something that's not mentioned in any trade-in advertisement. What really happens to your old appliance after it disappears from your home? Many major brands and electronic stores offer a trade-in program or free removal of old appliances when you buy a new one. For example, in the United States, companies like Whirlpool, LG, and Samsung have such programs, And in Europe, initiatives like the Waste Electrical and Electronic Equipment Directive are in place. The terms can vary. Some companies simply take the appliance, while others offer a discount on a new purchase. Whirlpool in the United States might offer a $50 to $100 discount on a new appliance for an old washing machine. LG and Samsung sometimes offer $100 or $200 as part of promotional programs. In Europe, some programs allow you to get up to 10% off a new appliance. But more often than not, the discounts aren't very large. Most companies view this as an environmental initiative rather than a way to attract customers. In many cities, there are electronic waste collection centers where citizens can bring old washing machines themselves. Often these centers work in cooperation with municipalities or private companies. In some countries, including Germany, the United Kingdom, and the United States, there are municipal services that provide collection services for large electrical appliances. For example, in New York City, you can order a free pickup through the NYC Safe Disposal program. Some companies are involved in secondary metal recycling, so they may buy the washing machine or take it for free. They send the appliance for dismantling, where they extract metal, electronics, and plastic. First, the machines are sorted into categories: working, partially working, and non-working. Working ones can be repaired and resold, while those beyond repair go to dismantling. Dismantling begins with removing the outer panels, doors, and drum. The motors, electronics, wires, and pumps are separated, as they can be reused or melted down. Metals are sorted separately: stainless steel, aluminum, and copper. Plastic parts are also sent for secondary recycling. This process can be done both manually and with the help of special automated lines that shred the casing and separate the materials using magnets and air separators. Automated lines for recycling washing machines consist of several stages, each responsible for separating different materials. First, the machines are fed onto a conveyor belt, where they are shredded by powerful rotary shredders. The blades of these shredders are capable of tearing metal and plastic casings into fragments ranging from 3 to 10 centimeters in size. After shredding, the materials pass through magnetic separators. They attract ferromagnetic metals, such as steel and cast iron, separating them from the rest of the components. Next, an eddy current separator comes into play, which uses a magnetic field to push out non-ferrous metals, including aluminum and copper. Plastic and light materials are separated using air separators. Powerful streams of air lift the light particles up, sending them into special containers, while the heavier ones remain on the conveyor. At the end of the sorting line, the remaining materials are additionally checked with optical scanners that analyze their composition and direct them to the appropriate sections for further processing or disposal. After the materials have been sorted using air separators and optical scanners, they go to separate processing lines. Plastic, metal, glass, and other materials are processed for further use or recycling. The remaining metals, such as steel parts, are sent to metallurgical enterprises for remelting and further use in the production of new goods. Magnetic separators effectively extract iron and steel, which are sent for remelting. Plastic parts are shredded and pressed into briquettes. These briquettes can be sent to specialized enterprises for the production of new plastic products, or for use as secondary raw materials for new technical devices. If the washing machine has glass elements, for example, doors or windows, they are thoroughly cleaned of any contaminants and can be melted down to produce new glass. The remaining materials that are not recyclable, for example, certain types of rubber or mixtures of materials, are sent for disposal or burial at specialized landfills. Such sorting and recycling lines significantly reduce the amount of waste that ends up in landfills and help return raw materials to the economic cycle. In some cases, for particularly complex materials, additional technologies are used, such as thermal decomposition or chemical treatment. They are used for materials that cannot be simply separated by mechanical methods, or that require additional processing to prevent contamination or harmful emissions. For example, some plastic components that contain a combination of materials, such as plastic with metal inserts or rubber parts. Such materials may not be subject to simple sorting and require special processing to separate the components. Often, rubber elements, especially with the addition of chemical compounds, are not effectively recyclable due to their complex structure. For such materials, thermal decomposition or other chemical processes may be used to break them down into simpler components that can be reused or disposed of. In some cases, when an appliance contains toxic substances, for example, mercury in old relays, batteries, or lighting devices, such materials must be processed by special methods. This can be a chemical process that neutralizes harmful components or isolates them for further safe disposal. Polyurethane or polyester materials, which are often found in wire insulation or in various components of household appliances, can be subjected to thermal decomposition to separate them into simpler components that can be recycled. In cases where washing machines or other appliances contain complex composite materials that have several layers of different substances, for example, plastic with metal or fibrous components, special processing may be required to separate these layers and for the subsequent recycling of each of them. In general, such technologies are used to ensure maximum efficiency of disposal and to reduce the negative impact on the environment, as improperly processed materials can lead to pollution or the leakage of dangerous substances. Every year, over 50 million tons of batteries are discarded worldwide, from small AA batteries to giant electric vehicle batteries. Imagine a mountain of metal reaching the size of Mount Everest, filled with toxic substances. But now, part of this mountain gets a second life. Behind the thick walls of factories, old batteries are put into shredders where steel blades tear them apart. They are frozen with liquid nitrogen and turned into a black powder that will once again become lithium or cobalt. Watch until the end. You will see how a new future for energy is born from waste. Battery collection starts with people. Private individuals turn in batteries from phones and laptops. Car service centers, batteries from electric vehicles, and also businesses that use a lot of equipment. Collection points are in electronic stores, supermarkets, or specialized collection centers. Here, everything is as manual as possible. People bring batteries, and staff or volunteers accept and record them. Old batteries from factories or car service centers are delivered by trucks to large collection centers. Special battery containers have sensors that determine the fill level. When a container is almost full, a signal is sent to the collection company. Some companies use drones to check the fill level of large containers in remote locations. Batteries are sorted by type by people and machines, because batteries come in different types: lithium-ion, nickel metal hydride, lead acid, and so on. They cannot be mixed during recycling. At small collection points, for example, in cities, batteries are sorted manually by workers. They rely on markings, labels, and appearance such as shape and case color. Small batteries from smartphones or laptops go in one direction, and large batteries from electric vehicles in another. At large enterprises, automatic sorting lines are in operation. Machines scan batteries by size, weight, and the type of metals they contain. X-ray analysis or spectroscopy is used to determine exactly which battery is in front of the machine. After scanning, the batteries move along a conveyor to different bins, where they await the next stage. Even at automated factories, people are present. Operators check whether the machines are sorting the batteries correctly. If a problem arises, for example, a torn battery case or a missing label, people intervene and sort manually. Batteries from electric vehicles or solar stations are too large for automatic lines. This is where robots come into play, helping to disassemble these giant blocks into smaller sections. Then they are sorted by material. No matter how much machines do, people are still the most important in the sorting process. These are mainly the workers at collection points and the operators of sorting lines. Specialists assess damaged batteries manually because machines cannot yet recognize all defects. Machines work faster, but for now, they can't do without people. Ultimately, every correctly sorted battery is a chance to recover rare earth metals and reduce environmental harm. Next, the batteries need to be shredded. They enter real metal jaws. The batteries are loaded into a machine that looks like a huge shredder, equipped with steel blades. The blades are so powerful that they can even shred the body of an electric car. Metal chaos ensues. The sound of tearing, grinding, and cracking. The batteries are literally ripped to shreds. Since the batteries can be charged, they first undergo freezing in liquid nitrogen. This cools the metals and reduces the risk of ignition. Some shredders operate in sealed chambers with inert gases to exclude contact with oxygen. There is also a more spectacular option. In some places, a controlled current is first used for ignition. The battery literally burns out, leaving only the metals. The batteries are shredded into pieces from a few centimeters to a crumb, depending on the type of shredder. The blades rotate at a speed of over 2,000 revolutions per minute, and metal fragments fly in all directions with a clang inside a protected chamber. The shredded pieces pass through magnetic separators, which with filigree precision extract ferromagnetic metals, for example, nickel or cobalt. Fragments of other materials continue their journey along the conveyor. A fine black powder, known as black mass, settles in special containers. This is where the treasures are hidden: lithium, cobalt, manganese. Machines literally suck up the powder with dust collectors to gather even the microparticles. Residues that are not suitable for recycling, meaning plastic and traces of electrolytes, are washed away with special streams of liquid. At this stage, hydraulic crushers are used, which turn the remnants into a slurry that is easy to filter. Engineers monitor the condition of the shredders and the temperature level inside the chambers. Specialists work with the results of the shredding. They check whether all the metals have been separated and whether any extra impurities remain. If a battery is charged and has defects, it can literally explode during shredding. But the system controls this. The explosion is extinguished by gases, and the process does not stop. After the batteries are shredded and that precious black powder is obtained, science in action, as they say, begins. The metals that seem to be hidden forever are extracted using two main methods: hydrometallurgy and pyrometallurgy. And although this may sound a bit technical, the processes themselves are extremely interesting. So what does it look like? Battery fragments are immersed in special acid solutions. There are huge tanks where a yellowish-green liquid is bubbling. This could be sulfuric or hydrochloric acid. During immersion, a reaction occurs. Lithium, cobalt, nickel, and other metals literally dissolve in this soup. To extract the desired metal, a clever trick is used: ion extraction. Special reagents, for example, organic compounds, are added to the liquid, which capture a specific metal, like a magnet. As a result, each metal settles into a separate layer. When the metals are separated, they are precipitated in the form of salts or hydroxides. They look like small white or colored crystals. For example, lithium precipitates as lithium carbonate, a powder that looks like fine sugar. Cobalt becomes a bright blue precipitate, and nickel, a pale green one. If hydrometallurgy is a gentle approach, then pyrometallurgy is more like shock therapy for metals. Here, everything literally burns and melts. The black mass is loaded into a huge arc furnace, where the temperature reaches almost 3,000 degrees Fahrenheit. The metals melt into a liquid mass, and the plastic and other residues simply burn up. The metals stratify, like oil and water, but at the temperature of molten lava. Several layers form in the furnace. Heavy metals, meaning cobalt and nickel, settle to the bottom, while lithium remains in the slag. This is the upper, lighter layer. Then this slag is broken up and processed separately to extract the lithium. After cooling, the metals take the form of small ingots, shiny, smooth, and ready for reuse. The cooling after the pyrometallurgical process usually happens in a controlled manner. After all, if you just let the molten metals cool on their own, it could take hours and sometimes even days. In addition, such cooling can create an uneven metal structure. This will affect the quality of the final product. Therefore, they are usually cooled in special chambers, where the cooling rate can be regulated. If the controlled cooling is air-based, the ingots are left on a conveyor under powerful fans. It's like a giant hairdryer that quickly cools the metal surface. If it's water cooling, for a faster process, the metal ingots can be immersed in a bath of water or special liquids. This is a huge tank where the red-hot ingot, upon entering the water, releases clouds of steam. It looks quite spectacular. Sometimes there is combined cooling. This is when some stages begin with air cooling and then are completed with water cooling to reduce stress in the metal. Controlled cooling ensures a uniform structure of the metals, which is critically important for their reuse in batteries. This reduces cracks or defects that can arise from sharp temperature changes. The obtained lithium is used to create new batteries, those that will charge electric cars or even your phones. Nickel can become part of turbines that generate energy from wind, and cobalt, an important component of medical equipment. So we are literally closing the loop. Old batteries give life to new technologies. Discarded batteries can turn into a real environmental disaster. First, they contain toxic substances that pollute the soil and water. Second, the mining of new rare earth metals not only depletes natural resources, but also harms the environment. Recycling solves both of these problems. You know what else is cool? The more batteries we recycle, the less we depend on mining new materials. This is a direct path to sustainable development. Despite the popularity of lithium, only 1% of this metal is currently recycled. The main reason is the high cost and complexity of the process. But researchers are developing new technologies that could change the situation in the coming years. Interestingly, even now, electric car manufacturers like Tesla, Volkswagen, and BMW are investing in their own recycling plant to maintain control over valuable materials. Every year, humanity creates energy that on one hand saves cities, and on the other, hides an incredible story of transformations. One average reactor produces 1,000 megawatts and requires only 27 tons of enriched uranium per year, the weight of 3 school buses. But to get these 27 tons, you have to mine and process over 100,000 tons of ore. In this video, we will follow the path from a noisy mine and acid vats to supersonic centrifuges, furnaces, and tiny fuel pellets. Every step is chemistry, giant machines, and unexpected risks that you are almost never told about. Stay until the end, and I will reveal one secret to you that will change your perception of atomic energy. An average American nuclear reactor has a capacity of about 1,000 megawatts. For it to operate for 1 year, it needs approximately 27 tons of enriched uranium fuel. 27 tons is the weight of about 3 school buses. And now let's compare. To produce the same amount of electricity, a coal-fired power plant needs to burn over 3 million tons of coal. That's over 10 million barrels of oil. Nuclear fuel is the highest form of energy concentration that humanity has ever created. But to get these 27 tons of fuel, you need to start with a much, much larger amount of raw material. The chain of transformations is simply staggering. To produce those same 27 tons of enriched uranium fuel, you need to start with 215 tons of uranium concentrate. And to get those 215 tons of concentrate, you need to mine and process over 100,000 tons of uranium ore. Imagine a giant mountain of stone, the size of a multi-story building, which ultimately turns into a volume of fuel that fits in one truck. This shows how dispersed uranium is in nature and how complex the process of its concentration is. It all begins in the roaring chaos of a uranium mine. Imagine a deep shaft or a giant open-pit quarry where huge machines with a deafening roar bite into the rock. The air here is thick with dust, and every stone that is brought to the surface looks absolutely ordinary, just a gray, dull granite or sandstone. The uranium here is invisible. It is dispersed in the rock in the form of tiny microscopic inclusions, and its concentration is incredibly low, often less than 1%. This means that to get 1 pound of uranium, you need to mine and process hundreds or even thousands of pounds of barren rock. Dump trucks, loaded to the brim, take this ore to a nearby processing plant that hums. The first stop is the primary crusher. This is a giant steel maw that, with a deafening crunch, crushes large stone blocks into pieces the size of a fist. Then, this crushed stone goes by conveyor to a huge mill. A giant rotating drum, filled with steel balls, resembles an industrial washing machine for stones. Here, in a continuous roar, the ore is ground into the finest, grey sand, almost dust. And now the real chemistry begins, a process called leaching. This grey sand is mixed with water, forming a thick pulp, and pumped into huge vats the size of a small house. A powerful chemical solvent is added to these vats, most often sulfuric acid. This acid, like a hungry predator, begins to eat the uranium, pulling it out of the solid rock and turning it into a liquid, dissolved state. This process lasts for many hours, while the entire mixture is continuously stirred. As a result, we get two things. On one hand, tons of wet, now unnecessary sand, so-called tailings, which are toxic waste, and on the other, a murky, greenish-yellow liquid containing our precious uranium. This liquid needs to be cleaned and concentrated. It is passed through a series of columns filled with special ion exchange resins. Imagine this as a high-tech water filter. The resins, like a magnet, pull out only the uranium ions from the solution, letting everything else pass by. Then these resins are washed with another solution, which washes the concentrated uranium off them. And so, finally, our final product is precipitated from this clean, saturated liquid. By adding ammonia or hydrogen peroxide, the uranium is forced to fall out of the solution in the form of a bright yellow, thick precipitate. This precipitate is filtered, dried in furnaces, and at the output, we get the same famous yellow cake, a heavy, radioactive, mustard-like powder. This is the uranium oxide concentrate, the first step on the long path to clean energy. The next step is purification to an absolute, almost unearthly purity. The yellow cake is sent to a special plant, where it is dissolved and, with the help of complex chemical processes, such as solvent extraction, all impurities are removed from it. The goal is to obtain perfectly pure uranium dioxide. But here the main problem arises, which is at the heart of all nuclear energy. In this perfectly pure uranium, 99.3% is the stable, lazy isotope uranium-238, which cannot sustain a chain reaction. And only 0.7% is the energetic, unstable isotope uranium-235, which is our fuel. They are chemical twins, and it is impossible to separate them by chemistry. To make the reactor work, we need to increase the concentration of this energetic uranium-235 from 0.7% to 3 or 5%. To begin enrichment, the solid uranium must be converted into a gas. It is treated with hydrofluoric acid, turning it into uranium tetrafluoride, and then with fluorine to obtain uranium hexafluoride. This is a very corrosive and dangerous compound, which has a unique property. It becomes a gas at a temperature slightly above room temperature. And so this gas, packed in special containers, is sent to an enrichment plant. Imagine a giant, noisy workshop the size of several football fields, filled with thousands of identical, tall, metal column-like devices. These are gas centrifuges. Each of them is a high-tech top that rotates at supersonic speed, making tens of thousands of revolutions per minute. When our uranium gas is pumped inside, the magic of physics begins. The heavier gas molecules with uranium-238, under the action of centrifugal force, are pressed against the walls of the centrifuge, and the very slightly lighter molecules with uranium-235 remain closer to the center. This is a microscopic difference, but it is enough. Special tubes take the gas from the center, which now contains a little more uranium-235, and send it to the next centrifuge in the cascade. And the depleted gas from the walls is diverted to the side. To achieve the required concentration of 3 or 5%, the gas must pass through thousands of such centrifuges. This is an incredibly long and energy-intensive process. When we have finally obtained our uranium hexafluoride, enriched to the required level, it needs to be converted back into a solid material suitable for fuel. With the help of chemical reactions, it is turned into a black powder of uranium dioxide. But this is not just any powder. Each of its particles has a perfectly calibrated size and shape. Now the most interesting part begins: the creation of fuel pellets. This black, heavy powder is sent to a press. Imagine a high-precision pharmaceutical press, only instead of medicine, it stamps radioactive pellets. It compresses the powder with incredible force, turning it into small, dense, perfectly cylindrical granules, or pellets. They are still brittle, like chalk. To give them strength, they are sent to a furnace. But this is not an ordinary furnace. This is a high-temperature furnace, filled with hydrogen to prevent oxidation. There, at a temperature of over 3,000 degrees Fahrenheit, these pellets are baked for many hours. During this process, called sintering, the powder particles fuse together, and the pellet turns into an extremely hard, dense, ceramic-like substance. It becomes so strong that it can withstand the extreme temperatures and pressures inside a nuclear reactor. Each pellet after this undergoes laser control, which checks its dimensions with micron accuracy. The next step is assembly. These small black ceramic candies are carefully, one by one, loaded into long, thin tubes. These tubes, about 13 feet long, are not made of steel, but of a special zirconium alloy called zircaloy. This material is unique in that it is very strong, resistant to corrosion, and most importantly, almost transparent to neutrons, allowing the chain reaction to proceed without hindrance. When the tube is completely filled with pellets, it is filled with an inert gas, usually helium, to improve heat transfer, and hermetically sealed at both ends. Now, it is not just a tube with pellets, it is a fuel element. And the final stage is the creation of a fuel assembly. Several hundred such ready-made fuel elements, for example 17 by 17, which gives a total of 289 pieces, are assembled into one large square bundle. They are held together by special spacer grids. This ready-made assembly, which looks like a giant, high-tech quiver with arrows, is the final product. It weighs about half a ton and is ready for shipment to a nuclear power plant. And so, having passed an incredibly long and complex path from an ordinary stone through chemical transformations, supersonic rotation in centrifuges, infernal baking, and precise, almost clockwork assembly, this concentrated bundle of energy is born, ready to quietly and reliably produce millions of kilowatts of clean electricity for several years. Imagine this. In the heart of the ocean depths, or in the roar of an airplane turbine, there is a part that decides everything. A single shaft, capable of transmitting the power of 1,000 Ferraris, or withstanding speeds of over 10,000 revolutions per minute. But how is this steel axis, which can lift a space shuttle, born from an ordinary cold ingot? And what do a ship's propeller, the size of a 3-story building, and the precision of a jeweler, removing a few grams of metal have in common? In this video, we will reveal the secret of creating giants, without which neither a ship nor an airplane can move. Watch until the end. A fact that will turn your understanding of the power of metal upside down awaits you. A shaft is a steel rod that transmits colossal power from the engine to the propeller. You can't just take any steel for it. Giant, perfectly clean steel ingots, each weighing tens or even hundreds of tons, are brought to the factory. This is not scrap. It is a special vacuum-degassed alloy from which almost all impurities have been removed. This massive cold cylinder is first sent to a furnace. But this is not a melting furnace. This is a giant heating chamber where, for many hours and sometimes days, the ingot is slowly and uniformly heated to a temperature of about 1,200 degrees Fahrenheit. It becomes dazzlingly yellow, plastic like clay, ready to meet the hammer. And so begins the most brutal and ancient art of metallurgists: forging. A giant crane picks up the red-hot ingot and places it under a hydraulic press hammer. This is a monster capable of dropping its top with a force of tens of thousands of tons, with a deafening, deep boom that makes the ground tremble. The hammer slowly but relentlessly descends onto the red-hot metal. These are not quick strikes. This is a slow, methodical squeezing. After each strike, a manipulator slightly turns the ingot. And so, strike after strike, hour after hour, the formless cylinder begins to stretch and take the shape of the future shaft. This process does not just change the shape, it does something incredible inside the metal. It compacts its crystalline structure and aligns all the grains of steel in one direction, along the axis of the shaft. It's like turning a scattered pile of straws into a tightly twisted rope. A shaft born in a forge will be many times stronger and more resistant to torsion than a simply cast one. After the forge, we have a rough, black, scale-covered blank that only vaguely resembles a shaft. It's time for the sculptor. It is secured in a giant lathe. Imagine a lathe half a football field long. The blank begins to rotate slowly, and a cutter of super hard alloy is brought to it. With a hiss and a screech, it begins to remove layer after layer, turning the black, uneven surface into a perfectly smooth and shiny one. A continuous ribbon of hot, bluish metal shavings, resembling a streamer, comes off the cutter. This process lasts for many days. Computer control ensures accuracy to the hundredths of a millimeter over the entire 30-meter length. Some shafts are made hollow to reduce weight. For this, a perfectly straight hole is drilled through its entire length. After final grinding, the surface of the shaft becomes as smooth as a mirror. Now that the spine is ready, it's time to create its heart, the propeller. This is a completely different story. A propeller has an extremely complex, aero or hydrodynamic shape that cannot be forged. Therefore, it is born from liquid fire, by casting. The main material for marine propellers is not steel, but a special bronze. It is slightly less strong, but it is not afraid of corrosion in salty seawater. First, engineers create a perfect computer model of the propeller. Then, based on this model, an exact full-scale copy is carved from wood or foam. This model is a true work of art. Next, this giant model, which can be as tall as a 3-story building, is buried in a huge pit filled with special molding sand. The sand is carefully compacted around the model, creating a perfect impression of its shape. Then the mold is disassembled. The model is removed, and we are left with a cavity inside the sandstone that exactly repeats the shape of the future propeller. This is our casting mold. Meanwhile, in a giant induction furnace, tons of bronze are being melted. It turns into a liquid, dazzling gold, boiling at a temperature of 1,800 degrees. A huge ladle brings this river of molten sun to our mold. And the foundry workers, dressed in silvery fire-resistant suits, slowly and carefully, through special channels, begin to pour the metal into the sand mold. This is a tense and dangerous moment. the metal must fill every smallest curve of the mold, leaving no air bubbles. After pouring, a long cooling process begins, which can last for weeks. When the metal has finally solidified, the moment of birth arrives. With a roar and clouds of dust, the sand mold is broken, and our propeller is revealed to the world. It is still ugly, black with a rough surface. It is sent for processing. First, the remnants of metal from the gating system are cut off, and then it enters the maw of a giant 5-axis milling machine. A huge milling cutter, controlled by a computer, for hours, layer by layer, removes the excess metal from the blades, giving them a perfectly precise, calculated aerohydrodynamic shape. But even after the machine, the surface is not perfect. It's time for manual labor. A whole team of workers with grinding machines, like an army of ants, for hours polishes each blade, bringing its surface to a mirror shine. Any unevenness on the surface of the propeller creates turbulence, which reduces its efficiency and causes destructive cavitation. And the final, most important test for both the shaft and the propeller is balancing. They are installed on a special stand and spun. Sensors detect the slightest vibration caused by imbalance. If there is even the slightest deviation, literally a few grams on a multi-ton part, it is eliminated by drilling tiny holes or removing a thin layer of metal. And only when this steel spine and bronze heart are perfectly balanced and fitted to each other are they ready to go to the port to be connected and begin their long service, silently and invisibly rotating in the dark to move giant ships across the oceans or lift airplanes into the sky. The engine of such a container ship can have a power of over 100,000 horsepower. Imagine the power of 1,000 Ferrari sports cars concentrated in one place. And all this colossal energy is transmitted through a single shaft to a single propeller. The torque on this shaft is so huge that if a lever were attached to it, it could easily lift an entire space shuttle. After final processing, the runout of the shaft over its entire length should not exceed a few hundredths of a millimeter. This is less than the thickness of a human hair. Imagine a perfectly straight line the length of a basketball court. Well, the real shaft does not deviate from this line by more than this microscopic amount, and the balancing of the propeller is generally a jeweler's work. On a 100-ton propeller, an imbalance of a few tens of grams is considered unacceptable. It's like finding and removing 1 grain of sand from the surface of a car. The turbine shaft in a modern jet engine, like the General Electric GE90 on a Boeing 777, is not just a rod. Its length is only a few meters, but it transmits incredible power. And the main thing is the speed of rotation. If a marine propeller makes about 100 revolutions per minute, then the high-pressure turbine shaft in a jet engine rotates at a speed of over 10,000 revolutions per minute. At such speeds, the slightest imbalance turns into a destructive force. Therefore, aviation shafts and turbine discs are balanced with an accuracy of fractions of a gram.